everyone, I am Nikhil of Group 41. So I am here to explain you applications of Bernoulli's number and Ricci flow. So Bernoulli's number, we have its first application that it can be used to express Euler-Maclaurin formula. You can see on this whiteboard how it is. I mean to say Bernoulli's number. Here Bernoulli's number are used. So here we use convention of Bernoulli's number where B of 1 negative is equal to minus 1 by 2. Bernoulli's number have some innovative application. When Euler first found this formula using Bernoulli's number, he used it to find the value of summation 1 by n square very easily. Now I will write a formula. Now we will see the second application of Bernoulli's number, and that is its use in expansion of tan and tan h. Let's see how it looks in tan x. Here mod x is always less than pi by 2. Until now we have seen about Bernoulli's number and their application, but Bernoulli's number don't have much real world application. They are just for asymptotic analysis and other thing. But Ricci flow is a concept which have many real world application whose alternative cannot be found. So I would like to tell you some of them, and some of them are it can be used in computer vision for tracking and registration of non-rigid surfaces. Next, it can be used for global surface parameterization in computer graphics, like in games. It can be used for brain mapping and colonoscopy, that is in medical imagery. Next, its application is Bernoulli's number are also used in brain mapping and colonoscopy, that are the fields in medical imagery. Next, it is also used for finding the solution for shortest word problem in computational topology. And next important use which is related to computer is that it guarantees the greedy routing and load balancing in a wireless sensor network. So these were some applications of it. But what is major importance of Ricci flow? So CMI give us 7 millennium problems. These 7 millennium problems were unsolvable, but one of them was solved. And one of them solved was Poincaré conjecture, and it was solved by some Russian mathematician. I think it was Gregory Perelman, and he solved it using Ricci's flow. Due to his understanding of Ricci's flow and using concept proved by Ricci, he was able to solve an unsolvable problem. He got 1 million prize and a Fields Medal, but he declined both. So thank you. Here are the applications of some mathematical concepts.
Hello, I am Yash, and I will tell you about the concept of Ricci flow. Ricci flow is an intrinsic geometric flow in differential geometry. It is a process that deforms the metric of a Riemannian manifold in a way formally analogous to the diffusion of heat, smoothing out irregularities in the metric. The Ricci flow was invented by Richard Hamilton in 1980s, and it was the primary tool to prove Poincaré conjecture, which is one of the 7 millennium prize problems, and Poincaré conjecture is the only one to be solved till date. As Ricci flow is quite an abstract concept, therefore first I will tell you about the curve shortening flow and relate Ricci flow to it. So what is curve shortening flow? If we want to deform this is a 2D closed path, and if we want to deform or move it, then we can do it in the following manner. We can draw a tangent along a point, and then this can be moved either in this direction or this direction. Now, how fast it will move? It will move according to the curvature of at this point, and curvature is defined as 1 by r, where r is the radius of the circle at this point. If here a small circle is being made, and here, if at this point a large circle is being made, therefore the curvature of this point is greater than the curvature of this point. And if we apply this the process of deforming at the points at each and every point, so at this point it will move, at this point it will move. One thing I forgot to tell is that if the circle being made is outside, then this point will move in outer direction, and if the circle being made is inside, then this will move in this direction. And so what will happen is the curve will get shortened up. This will become closer, this will expand outwards, and finally it will get converted in a circle. If we define the area in this to be constant, but if the area in this is not constant, then in this circle also at each point a force will be present, and it will transform into a smaller, keep getting smaller and smaller, and at a time the curvature will be very large, as the radius inside at each point will be infinitely small, curvature will be infinite, therefore it will turn into a singularity. Now this is about 2D surface. If we extend this idea to 3D surfaces, then we have to deal with mean curvature flow. In mean curvature flow, instead of tangent we make a plane, and the same thing happens there also. Now what is Ricci flow? Ricci flow extends this to various dimensions further than 2D and 3D. Ricci flow. Here, if this is surface, then in Ricci flow we do not think about inside and outside of the surface of this boundary. We only think about the surface, and we specify a function such that for each point, suppose I am taking this point, we define a matrix which is generally shown by G, such that it can be a square matrix or any matrix. This is called metric. These numbers tell in abstract manner the kind of information we want or we would like to have. If given a Riemannian manifold with metric tensor Gij, which I showed in previously, we can compute Ricci tensor Rij, which collects averages of the sectional curvature into a kind of trace. If we consider the metric tensor to be function of a variable which is usually called time, in this time is not the usual time that we understand, it is just a variable. The Ricci flow then may be defined by the geometric evolution equation. So this was all for Ricci flow.
Hello everybody, this is Kanak and I'm here to tell you about the great mathematician Jacques Hadamard. Okay. Jacques Salomon Hadamard was born on 8 December 1865 at Versailles, France. He died on 17th October 1963 at the age of 97 in Paris, France. He was a great mathematician in his time, known for his great works in number theory, complex function theory, differential geometry, and in partial differential equations. He obtained his doctorate in 1892 and in the same year was awarded the Grand Prix des Sciences Mathematicus for his essay on Riemann zeta function. He was also appointed the professor for astronomy and rational mechanics in Bordeaux. His foundational work on geometry and symbolic dynamics continued in 1898 with the study of geodesics of the surface of negative curvature. For his cumulative work, he was also awarded the Prix Bronzentilla in 1898, and he was awarded the CNRS Gold Medal for his lifetime achievements in 1956 before he died in 1963. One of his great works, the prime number theorem. The prime number theorem basically describes the asymptotic distribution of the prime numbers among the positive numbers. Now I'll explain you the basic statement of the prime number theorem. Okay, let us begin with prime number theorem. Okay, let pi x be a prime counting function that gives number of primes less than or equal to x. Okay, pi x is a prime counting function that gives primes less than or equal to x. Okay, for all x belongs to R. Okay, for example, pi of 10 equal to 4, which includes prime numbers 2, 3, 5 and 7, which are all less than equals to 10. Okay, so the prime number theorem states that the limit of the quotient of the two functions pi x and x by log x as x increases with bound is equals to 1. So mathematically it can be written as limit x tending to infinity pi x by log x equal to 1. Okay, so the prime number theorem states that x by log x is a good approximation of pi x as x reaches to infinity. So pi of x is approximately equal to x by log x. And one more thing, the prime number theorem can also be written as the prime number theorem is equivalent to the statement that the nth prime number Pn satisfies the relation Pn approximately equal to n log n. So this result is very important. So one example of this result can be let n is equals to 2 into 10 raised to power 17, as we have to take a n which is larger. So the nth prime number, which is 2 into 10 raised to power 7, is 8512677386048191063, which is approximately equal to 8.51 into 10 raised to power 18. As we can see, the value of n is 2 into 10 raised to power 17. So we calculate n log n, which is equal to 2 into 10 raised to 17 into log of 2 into 10 raised to power 17. So which we can see that which is approximately equal to 7.96 into 10 raised to power 18. So we can see that Pn is approximately equal to 7.96 with a relative error of 6.4%. So as x tending to infinity, the error will tend to 0. So this is the part of prime number theorem.
Hello, I am Omkar Verma, and today we will discuss about the mathematical fact Bernoulli numbers. Bernoulli numbers have been named after the famous Swiss scientist Jacob Bernoulli. He had used these numbers while solving the power sum problem. To describe the power sum problem, it is a sum of the r powers of the first n natural numbers, where r being a positive integer. So let's see how the Bernoulli numbers are used to solve the power sum problem. Okay, so now we will discuss the sum of powers problem. to describe Sm of n as sigma of n to 1. This means 1 is to m plus 2 is to m till n is to m. So the Bernoulli numbers give us a solution that we can rewrite them as a polynomial in n of degree m plus 1. So the coefficients of these polynomials are related to polynomial numbers by the Bernoulli formula. The formula is given as follows. The same sum Sm of n is equal to 1 by m plus 1 sigma m plus 1 combinations of k This is the Bernoulli formula, and over here we are using the Bernoulli numbers, and this is the Bernoulli binomial coefficient. If we test the formula for m equal to 1 and let's say n, so it becomes 1 by 2 b naught n square plus 2 b1 plus n1 equal to half n square plus n equal to, this is the general sum of natural numbers till n as we know it. The Bernoulli numbers can be defined as an integral of this format. In fact, it is a closed contour integral which takes n factorial by 2 pi I divided by e to z minus 1 divided by raised to n plus 1. And these are the Bernoulli numbers and the extent till infinity. As you can see, we have an alternating patterns of positive and negative numbers. That brings us to the derivation of Bernoulli numbers. There are mainly three types in which Bernoulli numbers are derived. First is using a generating function, second is using an explicit formula, and third is using a recursive definition. So now we will discuss all of them one by one. So now we will discuss the recursive definition of Bernoulli numbers. We define Bm of n as n raised to m minus sigma m to m minus 1 from k0, then combination mk, then the last number bk n divided by m minus k plus 1. Now for defining the first, for the zeroth and the first Bernoulli number, we will use the following definition. Delta denotes the Kronecker delta, and bk minus 1, bk minus and bk plus are two numbers. When you the binomial numbers are actually alternating between plus and minus, so at even places we get odd parity of. So some authors describe binomial numbers as they alternate between plus and minus. Some of them start from minus and some start from plus. Okay, so now we will discuss the explicit definition of Bernoulli numbers. As you can see, Bm of n can be defined as sigma m, then sigma to k, and the alternating of minus 1, k comma n v, and l plus v whole raised to m by k plus 1. Then again the same paradigm follows for the first and the second term, and the alternating signs are taken care of over here. This is the definition of Bernoulli numbers using generating functions. This is the first general form, and then as customary, the declaration for the first and the second elements. Here also we can see the alternating behavior of positive and negative signs. Okay, so now we will discuss some arithmetic properties of Bernoulli numbers. They are namely the Cummer's theorem, the von Staudt-Clausen theorem, and Ramanujan's congruences. Von Staudt-Clausen theorem states that for every n which is greater than 0, the b of 2n plus sigma of 1 by p is an integer. This sum extends over all the prime p for which p minus 1 divides 2n. The consequence of this is that the denominator of b of 2n
is given by the product of all the primes p for which p minus 1 divides 2n. In particular, these denominators are square free and divisible by 6. Now we come to the Cramer's theorem. The Cramer's theorem says that if the odd prime p does not divide any of its numerators of the Bernoulli's numbers b2, b4 and b of p minus 3, then x raised to p plus y raised to p plus z raised to p becomes 0. And this has no solution in the non-zero integers. These prime numbers are called regular primes, and we define the Ramanujan's congruences. The following relations provide a method for calculating Bernoulli numbers that is more efficient than the one given by their original recursive definition. As you can see, there are 3 cases for 3 different mod values by 6.
Okay, time for a fun fact. Almost all of us know that the first computer program was written by Lady Ada Lovelace for the analytical engine of Charles Babbage. But only some might know that the program she wrote was to compute the Bernoulli numbers in an efficient manner. This describes the significance of Bernoulli numbers in the history of computation. Thank you very much.